This next unit that we are covering is all about absolute value functions. So we are going to get started by, first of all, looking at what our parent function looks like. So the parent function of an absolute value function is f of x equals the absolute value of x. Okay, now to determine what our function looks like, you can see we have a table over on the left side. We're going to fill that table out and then graph those points and see what our parent function looks like. So first of all, x equals -5. Substitute that into our function. Remember, our function is f of x equals absolute value of x. So if I substitute -5, absolute value of -5 is +5. That means we have a point at -5, 5. Okay, then we substitute -4. Absolute value of -4 is +4. So our point is at -4, 4. Okay, so go ahead and fill this table in, and then we will continue by graphing. All right, you should have your table filled out. You can see I have my coordinate points, and now I'm just going to go ahead and graph those points. Okay, point at -5, +5, point at -4, 4, -3, 3, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. Okay, and you can see what our function is doing. It is forming that V shape, so I'm going to go ahead and connect my points, drawing as straight a line as I can. And remember, our function is non-terminating. We can assume it continues forever, so remember to end your lines with arrows at the end to indicate that it can continue growing. Okay, so now looking at the function domain, is there anything telling us that we cannot grow our function left and right? There's not, right? It'll grow infinitely. So our domain goes from -infinity to +infinity. Range of the absolute value function. You can see that our function starts at the origin and it grows infinitely. It's going to continue growing upwards. So we go from 0 to infinity, right? 0 is included, infinity is not. End behavior, as x approaches infinity, f of x approaches, remember, if it's growing upwards, it is approaching positive infinity. As x approaches -infinity, f of x approaches, now from right to left, you can see it's also growing upwards. So once again, it is positive infinity. And the vertex, where is the vertex of our function located? You can see the vertex at the origin. So vertex, this being a coordinate point, is at 0, 0. Okay. Now, the graph of f of x equals the absolute value of x is symmetric about the y-axis and therefore is an even function. Okay, meaning I can draw a straight line down the y-axis, okay, and you can see it's symmetric. This half here would fold over into this half here, okay. Now, graphing absolute value functions. There are transformations that can be applied to the parent graph, f of x equals the absolute value of x, just like any other function. We have g of x equal to a times 1/2, or sorry, times the absolute value of 1/2 times x minus h plus k. Anytime your function is written in standard form, such as this one here, your vertex is going to be located at the points h, comma, k. So this should tell you h is going to be a horizontal translation, and it is always the opposite. And I know this is going to be probably the most difficult concept to remember, right? But we always use the inverse of what is written in the function. K is going to be your vertical transformation, meaning it's going to move our function up or down. A is going to tell us whether we have a vertical stretch or compression, or if we have a reflection over the x-axis. So what we are going to do is we're going to look at each of these functions, identify the vertex, and at least one point on each side of the vertex. Okay, so looking at A, we have g of x equals the absolute value of x plus 2 minus 3. Okay, let's start by identifying the vertex. What is our vertex? So as you can see, we have positive 2 written, right? But remember, it is always the inverse of h, so it becomes negative 2. And then we have negative 3 as our k value. That stays the same. We do not change it. So our vertex is located at negative 3, or sorry, negative 2, negative 3. And I'm going to go ahead and plot that. Here's my vertex, okay? Now, how do we find points on either side? Well, we're going to pick values and simply substitute for x. One point, x value, to the left of my vertex is negative 4. So let's use negative 4, right? And I'm going to copy down my function absolute value, plugging in negative 4 plus 2 minus 3. And remember, order of operations works the same with absolute value. You do what is inside of parentheses, inside of absolute value first, and then you continue on with the rest of the problem. So in this case, negative 4 plus 2 gives us negative 2, still inside absolute value. Absolute value of negative 2 is simply positive 2, and positive 2 minus 3 is negative 1. Okay, so this is telling me we have a point at negative 4, negative 1. And I'm going to plot that. Negative 4, negative 1 is right here. And then we're going to do the same on the opposite side. So on the right side of my vertex, I'm going to use 0. Okay, so if I plug in 0, actually, let's go further than that. Let's go with positive 2. And again, it doesn't matter. You can pick your points. I'm just doing this to show you. So positive 2 plus 2 minus 3. 2 plus 2 is 4 minus 3. And absolute value of 4 is 4 minus 3 gives us positive 1, meaning our point is at positive 2, positive 1. Positive 2, positive 1, okay? Now, if you remember, absolute value functions have symmetry over your vertex. Your vertex is always that point of symmetry. So if I were to draw a straight line down the vertex, right, we would know that the left side would fold over onto the right side. So here's what we can do. We can use the points we've already found and create additional points, right? How do we do that? From the vertex, you can see I go up 2 over 2 to the left. Well, I'm going to do the same thing to the right side. There's the reflection, right? That point of symmetry. For my second point, we go up 2, 3, 4, and over 1, 2, 3, 4. So I'm going to go in the opposite direction. 1, 2, 3, 4. Reflections. All I did was create reflections of my points. Then we're going to go ahead and draw our lines. Remember, straight lines, as straight as possible. There's my right side. There's my left side. And I'm doing these as straight as I can. It's not perfect, right? But we're doing the best you can. Now, here's one thing about absolute value functions. You want to take up as much of the graph as possible. Here's what I've seen in the past that I don't want to see. I've seen people do little arrows just like this, and they stop. That's not taking up your whole graph. Okay, this is taking up my whole graph. You can see I go from one end of my graph to the other. Now, let's identify the transformations that took place here, okay? My A value, and there is always an A value, okay? Even though you don't see a number or a digit in the A value place, remember, there is a coefficient. There's always a coefficient. In this case, we have a coefficient of 1, so my A value did not do anything, okay? Our H value is negative 2. So because h is negative 2, that means that our function moved left 2 values, okay? And our k value is -3, which means our function moved down 3 values, okay? And if you think about our parent function, which we drew up here, our parent function begins at the origin, right? Our transformed function, we said left 2 and down 3. Well, let's test that from the origin, left 2 and down 3. And you can see that's exactly where our vertex is located, okay? Now, domain, are there any restrictions on our function? As you can see, there are none. So we go from -infinity to infinity. And for the range, where does your function begin? Our vertex is at -3, and we expand upwards to +infinity. Remember, -3 is included, so we use a bracket. All right, let's try one more. Let's try B, okay? Remember, vertex is at h comma k. In this case, x is alone inside of the absolute value, which means there is no h value, okay? Simply 0. K is +4, so my vertex is located at 0, 4. Now, what does that mean? If h is 0, did it shift left or right? No, there was no shift left or right. But k is +4, which means it moved up 4 units. Okay, plotting our vertex at 0, 4, we're on the y-axis. Okay, find a point to the left. So let's see, to the left of 0, I'm going to use -4. And it doesn't matter, you can pick any value you want. Absolute value of -4 is +4. 4 plus 4 is 8. So I have a point at -4, 8. There we go. And to the right of 0, let's use +4. Absolute value of 4 is 4. 4 plus 4 is 8. You can see this is a direct reflection of the first point we did, and that's okay because we spaced it out enough for us to be able to draw a good sized function. So connect our points. Remember to draw your arrows at the ends. Remember to take up as much of your graph as needed or as much as you can. In this case, it goes off our graph, so that's fine. And we have our function. Domain, are there any restrictions on our domain? You can see there are none. It's going to keep growing left and right. So -infinity to infinity. Range, where does your graph start? In this case, it starts at 4 and it goes upwards. So our range goes from +4 to infinity, not including infinity, bracket around 4, okay? All right, so go ahead and hit the pause button here and go ahead and try C. Find the vertex, identify the transformations, graph, and identify domain and range. All right, this is what you should have for C. You can see the vertex is located at 1, -5, which means we move right 1 and down 5. You can see for my additional points, I used -2 for x, found I have a point at -2, 2. And then I used 3 for x and found a point at 3, -3. Remember, you can always create additional points by creating reflections. So let me do this. Let me reflect these points so that you can see that it is still on point with our function, and they're going to lie on those lines. So creating a reflection of this point here, you can see that I'm 3 spaces away from my vertex. So I go 3 spaces to the right, and you can see it's going to cross through that point. This second point here is 2 spaces away from my vertex, so I go 2 spaces to the left, and you can see once again, those points lie on our function. You can use as many points as needed to create a straight line. The more points you have, the more straight your lines will be. Okay. Domain is infinite from negative infinity to positive infinity, and the range goes from -5 to infinity.